Hello everyone, welcome to the lecture series on Fundamentals of Generative AI and Large Language Models. We are in the week 5. In the previous session we had started with the GAN architecture, and then we had seen in detail how generator works and how discriminator works. In this particular session we will be looking into the GAN objective and then the loss function. Although some of the concepts will be repetitive, but you will have a complete clarity of the entire working mechanism of GAN mathematically in this particular session. Therefore, in this session we will be seeing what is the discriminator objective function, what is generator objective function, and together what is the GAN objective function. So, let us get started. So, if you look into this particular slide, here what we are looking is the discriminator, the loss function. Now, when you look into the discriminator has two parts. One where we will be passing the real samples. So, when it is a real sample, look at this, the training data set contains the real samples which are drawn from this particular distribution, that is from an unknown real data distribution. So, x is sampled from this particular distribution. What is the meaning of x is sampled? We are taking some samples from this distribution from the real data set, and then what is that we are doing? We are passing the data to a discriminator. Here if you see, x represents one single sample from the training data set. So, that x is passed to an discriminator. Here you can see from the diagram that x is passed to an discriminator, right. So, when x is passed to a discriminator, what is that discriminator has to do? You are passing in real samples, right. Therefore, the discriminator is going to produce this, which is nothing but what exactly is d theta of x? It is the predicted probability for the real sample x. So, therefore, d theta of x is a predicted probability that the input x is real. Now, just to recall from our previous session, if x is a real sample, what should be its ground truth? The ground truth should be y equal to 1, right. So, therefore, since x is a real training sample, its target label y is 1. So, because y is 1, now immediately recall, now we need to have a binary cross entropy function. So, we have this is the binary cross entropy. Now, y hat is the predicted 1. So, this is d theta of x, which is y hat, and y here is 1. Can we substitute all of these values into this formula? So, substituting y equal to 1 and y hat is d theta of x. On substituting, we are going to get this particular. So, the entire since y is 1, this term becomes 0. So, when this term becomes 0, 0 multiplied with anything becomes 0. So, we do not have the second term at all. Therefore, we are going to get for a real sample, the loss function what we are going to get is this minus log d theta of x. This we have seen in the previous session as well, but this is required for today's discussion also. So, first we will be seeing a quick recap. Yeah, so this is all about the discriminator loss for a real sample. So, this is the discriminator loss. Now, let us see what will happen when we pass the samples to a generator. Now, how do you pass the samples? What kind of samples we will be passing? The very first one is, you remember, first we take the z is an noise vector here. So, that z, from where do we take? Z is sampled from this particular distribution, noise distribution. So, we can also call this as a normal distribution, standard distribution, right. So, first z is sampled from this distribution, where z now becomes one random noise vector. Now, this z to what you will be passing? Z is now passed to an generator, right. The sampled noise vector z is passed to an generator. This is generator. Now, once z is passed to an generator, what is that the generator will give us? Generator will give us the generated data or generated sample. So, the generator produces the generated sample. This is what is the generated sample. We can even call it as an X hat or X fake. Okay, this is what we have obtained. So, we have now reached to this step. Once we get the generated sample, what is the next step? We have to pass it to an discriminator, right? The generated sample is then passed to an discriminator. So, when generated samples are passed to an discriminator, what is that discriminator has to produce? The discriminator has to give us this, right? What exactly is this? This is the predicted probability for the generated samples. So, the discriminator produces this. And what exactly is this particular term? This is an predicted probability for the generated samples. Once again, recall, if it is an generated sample, we got y hat. Now, you have to compare it with the ground truth. What should be the ground truth if it is an generated sample? Y should be equivalent to 0, right? So, look at this. So, since we got the generated, since this is a generated sample, the target for the target label y is 0. Now, once again go back and then take binary cross entropy. This is binary cross entropy function. For this, you take y as 0, and what is y hat? Y hat is this entire, the predicted value. So, substituting y equal to 0 and y hat this value into an binary cross entropy, we are going to get this, right. So, since y equal to 0, the entire term is going to be 0 here. The first term is going to be 0. So, what is that we are left out? We are left out with this particular. So, this is what is the loss function for a discriminator when the fake samples are given. So, this is what we have seen. Now, what is the next step? So, once we get the loss functions for real samples and generated samples, the total loss LD is the addition of L real and L fake or L generated samples. So, this is what is the total loss, LD equal to L real plus L fake. Now, we have already seen from our previous two slides that L real is given by this formula and L fake is this particular formula. Now, what is that we are doing? Just take these two formulas and then substitute for L real and L fake, we are going to get this. And since there is a negative, we are taking negative term common. By taking negative term common, we are going to obtain this. So, can we say that this is the loss function for an discriminator, where for a discriminator you are passing real samples as well as generated samples. So, this is the total loss of a discriminator. Now, if you recall from the basics, always we this generator and discriminator here are neural networks. So, what is the aim of a neural network? Ultimately, the aim here is to minimize the loss function. So, how is that? What loss you have to minimize here? Here you have to minimize the discriminator loss. How is that you will minimize the discriminator loss? You have to update the parameters. What parameters? Aim here is to update the discriminator, improve the discriminator, which means discriminator parameters have to be updated. What are discriminator parameters? Theta. Now, by updating discriminator parameters, is it not we are aiming to reduce the loss function here? So, this is what we are talking about. Neural networks are usually trained to minimize the loss function, and the discriminator parameters theta have been updated so that the loss becomes as small as possible. So, which means your aim is to minimize the loss. So, can we write the same LD? Now, can we write in this form? Look at this, it looks very complicated, but it is very simple. So, what exactly is our aim? Our aim is to minimize the loss. So, here minimize with respect to what? With respect to the parameters, and here parameters are denoted as theta. What is that you have to minimize? You have to minimize the loss function. Which loss function? LD, that is a discriminator loss function. Now, what exactly are these? There are two parameters. One is theta, second is phi. Theta is with respect to discriminator, phi is with respect to generator. Now, we we are updating the discriminator loss or discriminator parameters. If discriminator parameters are updated, generator has no role, phi will be kept constant. So this is what is this entire left sided term. So our aim is to minimize the loss with respect to the parameters theta, and what is that you have to minimize the loss function LD. And what is LD? Loss at a discriminator side. What are these two? These are the parameters. What are parameters we have? In this entire loss function, we have a theta as well as a phi. But since we are dealing with the discriminator, this generator part will remain fixed or frozen. You will not be dealing anything with respect to the phi. Now, what is this LD? LD is nothing but negative of this entire. So that is what is been written here. This minimum with respect to theta is retained as it is. This whole LD, the entire is being substituted by this particular formula minus of the loss. So this is what is the discriminator loss function. Now, if you recall once again, when we now whatever we have in terms of minimization, minimum of. So can you recall the concept? Minimum, if you want to minimize something, it is also equivalent to maximization of it. Right. So, if minimum of minus something is equivalent to the maximization of it, right? Do you agree to this? So, minimization minus AD is equivalent to maximization, positive one. Okay. So, now whatever we have obtained in terms of negative in the previous slide, can I write that in terms of positive? So, look at this. This is what we have obtained from our previous, where this is LD. So, minimization LD is equivalent to maximization. So, can we write in this way? The same one, instead of writing minimum minus, can I write a maximum here by using this particular concept? So, if a minimum is LD, maximization, can I denote it as capital VD? Right? V is a value function and D is at a discriminator side. What did we do? Since there is a math that we are entering, I will be slow and then I will be repeating here again. From our previous one, we had calculated discriminator loss for a real and discriminator loss for fake or generated. Then the total loss is given by LD is L real plus L fake. Now you have substituted the formula value and then you have obtained, there is a minus in both, you have taken minus out. By taking a minus, you have obtained this particular formula. We had obtained up till this. What is our ultimate aim of a neural network? Aim is to minimize the loss. Therefore, minimization with respect to the parameters theta, and the theta here are weights and bias if it is a simple neural network, or it can be the kernel weights if it is a CNN based. Okay. Now, minimization is equivalent to maximization. Therefore, whatever, if minimization is denoted with the term LD, since you have now converted into maximization, we are writing it as VD. That is where we have written here minimizing LD is equivalent to maximizing V value function and D is at a discriminator. I hope up till this point it is clear to us, right? Now, the next step is whatever the loss function that we have written here, this particular loss function is taking, this is only for one real sample and one generated sample. So, this is only for one sample, but when, so this is what has been written here. There is one real image X and one noise sample Z. But when you, during the training phase, it is not one single image that we will be passing to the model. We will pass a mini batch of samples, right? So during a training, we usually don't take one, we use many real and generated samples. If that is the case, the loss function cannot be just this simple. How is that you will be doing? Is it not for every of the sample you have to calculate this, and for many samples overall you have to take an average? So is it not this is what we are doing? For a real sample, we are now writing this term as expectation. What exactly is expectation here? Now what is this whole term meaning? We are taking many such x from where? From an real data distribution P data of x. For each sample we are computing this, and then we are taking the average of all of it. So is it not we are doing this? Take many samples x from a real data distribution P data of x, then compute this particular log d theta of x for each sample, and then take the average. Then you can ask the question, why is that we have written in this way? Can we also write this like this? Anyhow, you are adding all of this and then you are taking the average. So which is nothing but 1 by, that is you have taken, you are performing the summation of each of these terms, and how many ever samples you have taken, you are taking the average of it. So either you write in terms of expectation, or you can write in terms of average one, summation and average. This term is equivalent to this term. So this is with respect to real. What we have considered is this. But for a discriminator, we are also passing in generated samples, right? So for generated samples, how is that? This is the term for generated one, and here you are not considering one. You have said that there are many such generated samples. If there are many such generated samples, for each sample you compute this, and then you will take the average of it, right? So that is equivalent to this term. So in this particular slide, what is that we have understood? The minimization is equivalent to maximization. If minimization is denoted as LD, the maximization we will be denoting it as the value function for at a discriminator site VD. Now this is with respect to a single sample, but when you take an training, you will have many such real samples, many such generated samples. So for many real samples, you will be taking the average of, you will compute for each term and you will take the average of it. So we call it as an expectation. Same thing you are doing it for generated samples as well. So once this is done, now let us write what is the total value function or an objective function of an discriminator. So this is the final discriminator objective function. So if you see this, you remember we have LD is for minimization, but later we have converted it into a maximization. Therefore, can we write it as V and D? So it is VD, value function of a discriminator D. Now this term indicates here you have two, theta as well as phi. So this semicolon in this particular term indicates only theta is being optimized, while this phi is kept fixed. Right. So this is what we have understood during training and during back propagation. Only at a discriminator side, discriminator gets updated. During the training of a generator, the generator gets updated. Now what we are discussing here is the discriminator. So because it is a discriminator, the generator has no role to get updated here. So this particular parameters gets fixed. Right. So that is what is the left hand term meaning. Now what exactly is right side? What is this part? So here earlier we had seen for, if you go back, here we had seen for a single x and a single z. But what we are discussing here in the next slide here is for many such real samples and many such generated samples. So many real and many generated, is it not the expectation? So therefore we are writing in this form. I hope this is clear to all of us. Okay. Now, once this is done, what is our ultimate aim? Aim here is the discriminator is maximizing this objective function or maximizing this value function. So, now, so what exactly it is? Maximizing this entire term. So, rather than rewriting once again the whole equation, here I am showing maximizing this term, right, maximization with respect to parameters theta. Now, you can ask the question, why discriminator? For a discriminator we have used the term maximization here. Is it because from negative you have converted into positive or minimization to maximization, therefore you have got this maximization here? So, let us see why a discriminator always aims to maximize this. That is the point of discussion now. So, whatever we have seen in theory in the previous session, that will be made more clear here mathematically. Okay, what is the point of discussion? Understanding why discriminator maximizes this term. What a term? This entire. Now, look at this in this particular equation. Recall, a discriminator is the one where you are passing real samples as well as generated samples. Now, whatever the equation that we have written here is, one is for the real, this is for the real, and this is for the generated. So, both have been passed to a discriminator. Now, once again recall, for a discriminator, when real samples have been passed, what is the aim of a discriminator? It has to give the probability for a real samples closer to 1. Now, let us understand why it gives closer to 1. That part also will be made clear here. So, now, what we are discussing is the first term, that is the real sample term. For a real sample term, is it not we have to consider only so much, because this is the first term is something which is dealing with the real images. Why real images? Because you are passing x, x is the real samples. So, for a real sample we are considering the log d theta of x term. In this, what is d theta of x? Is it not the discriminator's probability, predicted probability that the input x is real? Okay. Now, when you take a discriminator and when you pass the real images, what should be the probability, what should be the output? The output should be closer to 1. So, that is where d theta of x value, the aim here is the desired output is the value d theta of x, that is the predicted probability value should be closer to 1. This is what is the aim here. Okay. Now, at the beginning you have still not started any training. So, initially you have randomly assigned some values. So, the theta value, whatever we have, the theta parameters, weights and bias are all randomly assigned. So, because of randomly assigned, now a real image is being passed to a discriminator. So, what will be the predicted probability? Do you think for the first time when real images have been passed, a discriminator will give the very high probability? No, because you have still not trained the model. How will the model knows which is real, which is generated, right? So, when samples have been passed, real samples have been passed, and at the beginning of the training, not necessarily that the discriminator has given a very high probability, not necessary. Let us assume discriminator has has given this particular probability 0.1, which means the discriminator is performing very poor here. Even for a real image, the probability value is very, very small, which means only 10% it is saying that it is real. No, it is not correct, right? So, and why this is happening? It is at the beginning of the training where you have still not started a training and the parameters are randomly assigned. So, because of this d theta of x, the predicted probability value is very poor, and here it is 0.1 for an example. Okay. If this is 0.1, what is our function here? It is log d theta of x. If d theta of x is 0.1, this log 0.1, what is the value? We are getting very low negative value. It is very low value here, right? So, now, so with this, what are we understanding? Is it not just with this value minus 2.303, is it not we are understanding that discriminator performance on real images is very poor, right. So now that is being passed as a feedback to a discriminator, gradients in the form of gradients. Now over a period of time, is it not that discriminator gets trained? So after some training, say for example, the discriminator has given this particular probability 0.5. Now, when a discriminator has given this particular probability d theta of x, now what exactly is log 0.5? The log 0.5 is this. Is it not we are minimizing the value? Earlier from this value to this value, you see, is it not we are improving? Can we say in this way? Now next you see, again over a period of time, the discriminator has further improved. So discriminator value is now 0.9. For example, after a certain iterations of training, now discriminator has for a real images, discriminator has given this particular probability. Now after you obtained 0.9, again you calculate the loss function. What is loss here? Log 0.9. Is it not we have obtained this value, right, which is now closer to 0? So is it not now you are increasing the value? Ultimately aim is to maximizing. What is that you have to maximize? You have to maximize this term. So is it not from here you have improved? From here you have improved, right. So now you are maximizing this value. Now go back and then understand this. What is that we have written? We have written log theta of x, which is written here. Now what is that you should substitute here so that we get the maximum value? So what is the value that you need to substitute? Here it is the probability, right? Probability is at the most it can give the value between 0 and 1. So can I have, if this entire term is equivalent to 1, then log 1 is 0, right? So did you get this concept? This is important. Whatever we have seen in the previous theory, that will be made clear here. We are saying that discriminator should maximize this term. If discriminator has to maximize this term, for what the discriminator has to maximize this term here. For what value of this discriminator, this log term will be maximum. So since it is a probability for a real image x, when you pass, either it can predict the value 0 to 1 only, right. So if you want this log term to be maximum, which means this d theta of x should be 1. This is the maximum value that it can give. I hope this concept is clear to you. That is the reason why d theta of x model going to give this as 1. Because ultimately it is not exactly 1, it is closer to 1, maximization, because as d theta of x increases, log d theta of x also is getting increased. You see, from 0.1 to 0.5 to 0.9. So d theta of x is getting increased. As this value is getting increased, look at this, minus 2.3 to minus 0.6 to minus 0.1. So as the d theta of x increases, log value is also increasing. But what is the maximum limiting value where d theta of x can be only 1, at the most it can be 1. If this is 1, you are reaching to a maximum value, log 1 is 0. Therefore, maximizing the real image term pushes d theta of x value closer to 1. So I hope this is clear to you. Now let us see what exactly happens for an generated samples. So for generated samples, which means we are now dealing with this entire concept, this entire term. Now what exactly it is saying? You have to maximize this term. If you have to maximize this term, what term? Log of that entire. If log of that entire has to be maximized, what should be the best possible value of this so that that entire log term will be maximized? That is what we are discussing. So, if you recall, we are since we are dealing with generated samples, we are considering this term. In this, what exactly is G5 of Z? This is the generated sample. That generated sample is then passed to a discriminator. What is that discriminator will give? Discriminator will give the predicted probability for the generated samples. Okay. Now recall, it is a discriminator. For a discriminator, you are passing an generated samples. Therefore, its probability value should be closer to 0. This we know it very well. Now, if this value is closer to 0, which means we are now saying that d theta, this entire term value should be closer to 0, then you are going to maximize this term, is what we are trying to understand from this. Now, let us see why, in which scenario we are going to maximize this. At the beginning of the training, definitely discriminator is not very well trained here. So, initially discriminator may incorrectly classify it, which means when you have passed and generated samples, ideally it has to give the probability closer to 0, but not necessarily, right. So, because weights are randomly assigned, let us assume that for a generated sample, discriminator has given the value 0.9, right. If this is the predicted value, what is there in the formula? It is 1 minus, because it is 1 minus. So, look at this, 1 minus 0.9 is a smaller value, that is 0.1. Now, that smaller value you pass it to the log 0.1, is it not you are getting an very low negative value, right. You have obtained very low negative value here. So, which means discriminator performance on the generated samples is very poor, right. So, what is that we have to do now? So, next is as the training progresses, after some training, let us now assume the discriminator has produced this particular value, right. For what? For a generated sample, discriminator has given this particular value. Look at this, 1 minus this you have obtained 0.5, log 0.5 you have obtained this. Okay. After further training, so let us assume now discriminator has given this particular probability, right, 0.1, which means discriminator probability is now closer to 0, right. If it is closer to 0, it means it is very good. When this is closer to 0, 0.1, 1 minus 0.1 is 0.9, log 0.9, look at this value. Are you getting at what we are discussing? Ultimately, our aim is to maximize this term. If you have to maximize this term, what should be the value? The maximum possible value, this should be 0, then 1 minus 0 is 1, log 1 is 0. Right, that is the maximum value, which means this term should have a value closer to 0. Is it not? We are seeing all of this here. If you look into the previous one, here initially the value of what we have obtained is 0.9. It is very high value. From there you have obtained this value. Again, when you further go, when you look into this, here you have a value 0.5, then you have obtained this value. Further you have got 0.1, which means you are now moving closer to 0. When you are moving closer to 0, look at this term, right. This is also this value of what exactly is happening here? What is the relationship between 0.1 as you are decreasing the value? What exactly is happening to log value? Is it not log value is increasing? You first had minus 2.3 to minus 0.6. Now it is minus 0.1. Is it not now moving to 0? So, is it not as the predicted value decreases closer to 0, log value is increasing? So, you see here, finally, we have to maximize this whole term. If you have to maximize this term, for what value you are going to get the maximum value? So, this value should be closer to 0, then only 1 minus 0 is 1, log 1 is 0. right? I hope this is clear to you. So, that is the reason why the discriminator pushes this particular term closer to 0, right. What is the relation? As I said, as this value decreases, 1 minus this term increases and the log term increases. What is our ultimate aim? Aim is to maximize this term. What term? The discriminator is, the aim is to maximization. So, if it has to maximize, we have understood already how this is maximizing. Now, we are understanding how this term has to be maximized. So, if your aim is to maximize log of this entire term, that is possible only when this value becomes closer to 0, right. So, that is the reason why discriminator maximizes the value function. I hope now it is clear to you. From theory, we have seen that for a real image, the predicted probability should be closer to 1. For a generated images, the predicted probability should be closer to 0. So, that is what is being made clear from this. Now, so with this, we have now come to an generator objective function. What should be the generator objective function? You see how it is being written, because it is a value function for a generator, we have written it as Vg, and it is a generator. Now, your aim is to improve the generator one. So, therefore, generator parameters are optimized, theta, that is discriminator parameters are fixed, and we will have only one objective function here. Overall, this is for the real images and this is for an generated images. So, for the same, now let us understand what exactly is generator objective function. So, in this entire, if you look into the first term, that is this term, it is all with respect to real images and then the discriminator. So, when you are dealing with the generator part, we do not have any work with respect to first term, right. Look at this, the first term contains only the real samples and then the discriminator part. Therefore, it does not depends on generator parameters phi. Therefore, generator cannot change anything this with respect to this first term. Now, let us see when you are training the generator, what exactly comes into the play? It is only the second term. So, second term has the generated samples. Therefore, during the generator update, we optimize only the second term. We optimize only this term. Okay. Now, recall from our theory concept, where you are now dealing with generator, your aim is to improve the generator. Now, generator has generated the samples. This generated samples are given to a discriminator. What is the role of a discriminator? Now, here for a generated samples, we are discussing at a generator part. So, when generator has generated the samples, when it is given to a discriminator, discriminator should give the high probability. Right? Why it has to give the high probability? When it gives the high probability, then and its ground truth is 1 there. Therefore, when you compute the gradients and when you give that feedback back to the generator now understands that, okay, whatever images I am generating, those images are realistic images. Correct? So, which means for a generated samples, the aim is discriminator should give the high probability. So, let us recall whatever we have seen. The generator wants the discriminator to classify the generated samples as real, which means the probability of this should be closer to 1. Right? Now, if this value is closer to 1, what exactly is the problem? Go back, this value should be closer to 1 is what we are saying. If this value is closer to 1 or 1, 1 minus 1 becomes 0. So, is it not this term becomes 0? If this value is closer to 1, 1 minus 1 value is closer to 0. If this is 0, what happens to log term? Log 0. Log 0 is undefined. So, this entire term has become now 0, log 0 is undefined or it is minus infinity. Then what is the aim? What is the aim of a, the aim of a discriminator was to maximize. What is the aim of a generator now? Is it not? It has to minimize this particular term. Log this entire term has to be minimized. So therefore, you see here, so the generator tries to make this term as small as possible, this particular log of this entire term as small as possible. Therefore, the aim of an generator here is to minimize this entire term. Okay. So if you have to visualize, you can see this. Ultimately, the aim here is this value should be closer to 1. So as this value gets closer to 1, look at this, what exactly is happening? The value is getting minimized, right? Minus 6 is the value is very small here. So this term is small. So therefore, the generator objective function here is to minimize. So I hope this is clear to you, although it is very complicated concept, but it is as you understand, you will be able to get this concept clearly. Okay. With this, let us see what is the GAN overall GAN objective function. What we have seen in the beginning of the session is discriminator objective function. Aim here is to maximize, right? The discriminator objective function is to maximize with respect to theta. And just some time back in the previous slide, we have seen what is the aim of an generator. The aim of a generator is to minimize. So the aim of a generator here is to minimize with respect to phi. But when we take a GAN, here we do not have independently generator, independently discriminator. We have generator, discriminator entire together as one. So combining both gives a original GAN min-max objective. How is that you will combine? One is minimum, second is maximum. Right. The aim of a generator is to generator here is to minimize, and the aim of a discriminator is to maximize. So you are combining both of these. By combining both, we are obtaining it as a min-max. So can we now write this as min-max? That entire V is whatever we have seen so far. Right, this is this entire is the V. Now here 5 is with respect to G, theta is with respect to D. So can we write in terms of G and D? So therefore, one is minimizing and one is maximizing. So therefore, the goals here are opposite. What are the what is opposite here? Now discriminator wants the generated samples to give the probability closer to 0, but generator wants the same generated samples to receive the value closer to 1. So is it not there are two opposite objectives here. For a generator wants whatever the samples generated samples I am receiving, I should give the probability closer to 0. But what is generator expectation? Generator is saying that whatever images I am generator is generating, when we give it to a discriminator, discriminator should give the high probability. So one is minimizing the objective function, the second is maximizing the objective function. Therefore, go back and then understand, we have A is adversarial. What is adversarial here? Is it not two are competing with each other? One is minimizing, second is maximizing. So this is all about the GAN, the architecture diagram, and then understanding the same architecture mathematically. So this is the objective function. With this, we have come to an end of this particular session. In the next session, we are going to see a very small topic called GAN convergence and equilibrium. Thank you.